All right, welcome everyone. So we are going to continue our journey into chapter 6 today, which we barely started last Wednesday. But before that, just a couple reminders that our first test is going to be Wednesday and Thursday of this week, the 14th and 15th. It's going to be in the ballpark, 25 questions, maybe 26 or 27. I have it built. It's just a matter of whether I want these 1 or 2 questions in there. Your review is 27 or 28 questions. You'll have 90 minutes to take the test. It'll be located in the quiz and test section of my math lab. So here's my math lab. You'll go to quizzes and tests, and on those 2 days, the very first thing you'll see up here above all these skills checks is the test. It's the only assignment you'd have access to at the top. So remember that for that, it's due by 11:59 p.m. on the 15th. So you have to start and submit your test before then. There will be a location in Canvas, and I'm going to put it above the video links on those 2 days where you'll submit your work. It should be pretty easy to tell. You just go in there and it'll ask you to submit a file, and you submit your file, pictures, whatever. You have to get that submitted within 15 minutes of finishing the test, and that's just to curb any kind of foul play. You get 1 attempt on this test, so make sure when you take it you're ready. I have put up the review as of this morning, and I finished it about 8:30 this morning. It's in the homework section that will be comparable. So homework, which we were already in, 5.7, 5.8, chapter 5 review. So I'm not going to put a due date on it because it's not an assignment that you have to do, at least for now. I think I've mentioned that if I find that none of my students do the review, then I will make it mandatory. But it still wouldn't be part of your grade necessarily, but you'd have to do it to take the test. Do the review. It's not going to hurt you. It's got all the guided stuff like the homework. Question help, that is to say, these things that you won't have during the test for obvious reasons. Remember that the test is supposed to be your own work. This is going to be a no calculator test, which means I basically can't do any of the application problems except for one of them, I think, because most of them require calculators, but I don't want you to have a calculator for all the other stuff. So we'll find a way to assess that later. So again, that's all the information for the test. We will still have class on Wednesday from 12:30 to 1:45. So we will still have a lecture. So maybe you take the test before or after the lecture. Maybe you wait till Thursday. I know most of my students like to wait until the last few hours, but you do it whenever you're ready. But there will be no exceptions to this 2-day deadline unless you have a doctor's note or something like that. Not just an email and say, oh, I missed it for whatever reason. I need a legit excuse with documentation if you miss it. Once you submit your test and your work, if there's a question that you think you deserve partial credit on, you can email me about it, or a few questions. Don't give me half of the questions you do, though. Given the format of this test, I am a lot less lenient on partial credit for obvious reasons, but I still do give it occasionally if you bring it up. All right. So we're done with that. We're done with that. All right, back to 6.1, verifying trig identities. So we said trig identities are equations that you must make the left and right side match. You will do this by using various trig properties seen in the last chapter. An identity is only verified once the sides match. Now, in the homework and the test, this feels a lot less traditional. It's another one of those cases of I really much prefer just blatant paper pencil versions of this stuff. But for simplicity's sake and not being face-to-face, we're dealing with what we got to deal with. So my math lab homework tends to drag you more by the nose, and it gives you like the 4 steps and what they kind of look like with just certain pieces missing. And they'll give you a drop-down menu over what thing you should do to make the next thing happen. Like, should you use a Pythagorean identity, or should you use even odd properties, or should you turn everything into sines and cosines? What do you think? That kind of idea. So that's what the homework problems will look like, and that's what the test problems will look like. However, for the major or for the more important major understanding of the topic, I'm not going to do my problems like that. I'm going to teach them the traditional way, the way that you should understand how to do them, because this stuff can creep up when you're in calculus every now and then. But it really stresses the importance of knowing your Pythagorean identities. That, you know, we don't really like things most of the time unless they're in sines and cosines, so that's a common way to simplify them. Factoring, the various different methods for factoring, so that'll come back in an even more complicated form. Combining fractions by getting an LCD, splitting fractions. Clearing fractions is an option I don't actually have up here, but it is a good option. Instead of combining fractions, you could clear fractions, which means multiply all the tops by the entire LCD. Use your even and odd properties. So cosine is even, sine and tangent are odd. So if you add a negative inside of one of them, you generally end up having to pull it out using one of those two properties. If you have a fraction that you just have no idea what to do with, maybe it's the only fraction, maybe try multiplying top and bottom by its conjugate. Cross multiply if it's just one fraction equal to another fraction. Try and just handle one side instead of both sides. Now this one right here, this is really what the homework and test problems will kind of emphasize, really only focusing on one side at a time. And then we said starting over is an unfortunate just side effect every now and then that we have to deal with. We might hit a dead end, or it might just be something we don't know how to handle and we need to try a different approach. So starting over, I cannot tell you how many trig identities I have started over in my lifetime. More so as a student, but as a teacher, it still happens every now and then. Nobody's perfect. All right, that's all we have there. How much room? We got a decent amount of room. So these basic tips, make sure you have all of them down. You can even throw in that extra one I mentioned, which was clearing fractions. And I'm not writing down all the, and I say this lightly, baby algebra, like what you do with your LCD and all that stuff. You should know that. That's why we're pre-calculus students, not Algebra 1 students, or not even arithmetic students. Okay. Example 1, sorry, I don't know why that just happened. Example 1, verify. The only instruction I'm given, verify. And for this one, we're going to do cosine squared of theta, parentheses 1 plus tangent squared of theta equals 1. So this is a trigonometric identity. The left side and the right side are identical. Believe it or not, that left side is equivalent to 1. Now, you probably don't automatically see that. I know I automatically don't see that. So we've got to take a couple of simplification steps to show that. Kind of like if you add x squared plus 5x squared plus 6x squared, you'd have to add the 1, the 5, and the 6 to get a 12, and then you'd simplify to 12x squared. That's the point of this. The point is not just making the left side match the right side. The point is, later when you're in calculus, if you have something like just this, that you would say, all right, well, let me try some trigonometric manipulations to see if I can just make it look a little prettier. And it turns out you can. It turns out it would be 1. That's the ultimate point of this. All right, so verify. What can we do? Well, I'm going to try, I see tangent squared, so some people might say we'll turn that into sines and cosines. I will do that in the next version of this example, though. I really think it's important that you do have these 3 properties in your heads at all time, because you might see variations of them or things that you can simplify with them. So in fact, one of them is up here. 1 plus tangent squared is the same thing as secant squared. So maybe applying that Pythagorean identity would be helpful. So let's do, I'm just going to write some abbreviations, Pyth for apply a Pythagorean identity, particularly the middle one. 1 plus tangent squared is secant squared. But Mr. Beckner, the 1's written in the wrong order. Oh, you silly student, you should know that addition order doesn't matter. All right. So the 1 plus tangent squared in blue, I'll show what I'm changing to. I'm changing it to secant squared of theta. And like I said, usually when I talk, I don't say the angle, but make sure you do write it. Everything that didn't change, I'll stay in black. Cosine squared of theta, and then equals 1. And this is, of course, at times if you need to show that. But if you don't put that dot, when you have a trig function sitting next to another trig function, it does imply multiplication. You could be really tedious and wrap each in parentheses, but that's just overly silly in my opinion. All right, so cosine squared times secant squared. What could we do next? Well, there's a few things we could do, but I would say the easiest out of this list, I'm trying to keep the list up here as best I can. Maybe if I zoom out a little. There we go. Turn everything into sines and cosines. Now, that was the thing I said we'll do in the next example first, but this time I'm going to do it second. So the first thing we applied was a Pythagorean identity. Now I'm going to turn everything into sines and cosines. And no, I'm not writing tangent there. I'm just saying I'm expressing everything in terms of sines and cosines. So the cosine squared I'm not going to change because it's already in sines and cosines. This, the blue ink, I will be changing. Please keep, go ahead, but in the future, keep questions in the chat. I appreciate that.
Oh, sorry.
No, it's okay. Go ahead.
Couldn't we just divide the left side by cosine squared and the right side by cosine squared and get the Pythagorean identity there?
That would be the reciprocal definition of cosine or secant, whichever you prefer. But yes, you right there have shown the point I made at the end of last class and what I will be doing today, that there can be 10 or 20 different ways to verify each of these. So that was an excellent point. So what was mentioned was that we could just divide both sides. I'm going to erase this after I do it by cosine squared. And what you would get is that the secant squared is equal to 1 over cosine squared, which 1 over cosine is secant. So that would be secant squared equals secant squared. And that's when you would be done. So that is an excellent observation that would get you full credit on the test. But like I said, I have just a couple of particular ways I'm going to be doing these, but I do encourage open thoughts and thinking outside of the box, all that normal stuff. All right, so we're just going to change the secant squared to, well, secant we just said is 1 over cosine, so secant squared would be 1 over cosine squared. Oops, wrong color. So again, blue for what's changing. So this would be times 1 over cosine squared of theta. Then we have our equals 1. Now again, in terms of formal proofs, this is not done because you haven't shown the cancellation. You say, oh, well, cosine squared in the top, cosine squared in the bottom. And what that gives you is, whoops, those cancel. Now I'm going to erase the cancellation. And that just gives us a 1 on the left side because everything else is gone. So 1 equals 1, and this is when we are done. The left side and the right side match. If you are going to go further down the road in math, what you might see a lot of people do is they'll write QED. This is Latin. I'm not going to spell it because I'll misspell it, but it's quod erat demonstratum, which literally means, translated, that which was to be demonstrated has been. Quod erat demonstratum. It just says, we demonstrated what you said to do. We did what you asked. We made the sides match. But a lot of times when you talk about proofs in math, they love QED. QED means you're done. You finished it. Everything's accurate. Now, what a lot of fake mathematicians, I'll say, might like to do is they'll, just fudge point something somewhere and, oh, well, yeah, sure, this is that, and then it's done, and then write QED, and they say, well, since I wrote QED, it's done and it's accurate. But then someone goes in and goes, well, no, what you did here was wrong. It's not actually wrong. I'm just saying someone would do. That was right, so don't misthink there. But that's what an official verification looks like. This is one of the many, 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 many different ways this one could have been done. The downside of the technology here is, while there's really about 20 different ways to solve this one, to verify it, not solve, my math lab is going to take you through one specific type. So they'll probably do this and then that, or maybe they'll do it as the alternate approach I'm about to take. So an alternate method, so which we already went through one and erased it, where we divided both sides by cosine squared, or we could have divided both sides by secant squared. There's all sorts of different things. You could inject Pythagorean identities from there if you really wanted, but it would just take the problem 5 times as long to do. All right, so the first time I did the Pythagorean, then I did the sines and cosines. But the problem there is a lot of people don't remember that this is secant squared. So if you were a student who forgets that secant squared, maybe instead of doing Pythagorean first, maybe you switch to sines and cosines first. So we have our, all right, cosine squared times 1 plus tangent squared equals 1. So I'm going to switch to sines and cosines. Let me zoom back in so I don't have to write so teeny. So the cosine squared is fine. I'll leave that alone. But the 1 plus tan squared is going to become 1 plus sine squared over cosine squared. If tangent sine over cosine, tangent squared is sine squared over cosine squared. And by the way, I'm not trying to discourage anyone from asking questions earlier. If you have to ask that way, that's fine. But I do just ask to try and keep them in the chat. Again, not discouraging questions. I appreciate them. Okay, so, well, now what you could do is you could distribute if you wanted to. That would be one thing to do. So this cosine squared, you could give it to both terms inside. Just an algebraic simplification potentially. So cosine squared times 1 would be cosine squared. That's supposed to be blue. And then distributing the cosine squared to this fraction. I know this might be confusing, but this cosine squared is this cosine squared. Now the one that was originally a fraction, I'm going to write in black. So this right here is this. I'm going to erase the circles in a second. Remember I said the blue I was trying to keep to the new thing, so that was the distribution. All right, erase. Go. All right, well, this right here, cosine squared times sine squared over cosine squared, you can cancel. There's a cosine squared in the top and in the bottom, kind of like there was over here. So those will cancel each other out, which I forgot to write the word cancel last time, cancel. So that's just going to give us cosine squared of theta plus, now that's just a sine squared of theta. And yes, I know sometimes my thetas end up looking like 2's, please forgive me. And then what happens here? A lot of students on a old school paper pencil test, they'll stop here and they'll say QED. Oh, I said QED, I'm definitely done. And then they get their test back and they've lost a couple points because that's not right. Yes, it is true that cosine squared plus sine squared is 1, but you haven't verified it. You verifying it means you need to write the left side. You need to use your Pythagorean identities that sine squared plus cosine squared is equal to 1. Now we see the left side match the right side. Now we're done. Now we can say QED. That which was to be demonstrated has been. It doesn't mean that the answer or the final equation has to be 1 equals 1 or 2 equals 2. It could be sine squared plus cosine equals sine squared plus cosine. That would be done. Excuse me for a second. All right. So 2 ways. One of them involved a distribution, but both of them, well, the other one didn't, both of them ended up using Pythagorean and sine cosine and some kind of canceling. It's just a different order and a different Pythagorean identity. This Pythagorean identity, that was weird. This Pythagorean identity is one that people tend to know less, but you should still know. This Pythagorean identity is one that everybody knows, or I don't know how you pass this class without knowing that. It might be possible. So many different ways to get these problems done. Now, some problems are really bad, and it seems like there's only one easy way, but that doesn't mean there's only one way. It just means there's only one easy way. So again, I don't really like the fact that the homework, again, drags you to one particular way, but at least it is detailed enough for you to follow. And I give lots of examples so you'll see all the different variations they could do to you. All right, B, cosine squared of theta minus sine squared of theta is equal to 2 cosine squared of theta minus 1. So you might say, oh, the left side's 1, right? The left side's 1. Well, no, that would not be right, because that's not sine squared plus cosine squared. It's cosine squared minus sine squared. What's interesting is that's actually another identity we're going to learn later, but not quite yet. So there's a couple things you could do here. I'll describe some things that I'm not going to write down, at least for the first run. I could move things from side to side. This is an equation. Nobody said you can't move things from side to side. So maybe you move the cosine squared to the right, or the 2 cosine squared to the left, or the sine squared to the right, and the 1 to the left. I mean, you could do all sorts of different things to this in an attempt. But for now, I'm not going to do it that way. Again, I'm doing some of these 2 ways, so maybe I'm going to do it the second way. The first thing I'm going to do, and it's not super obvious, I'm going to do a Pythagorean identity. You go, how are you going to do that, Mr. Beckner? The Pythagorean identities are these 3 things. Obviously, we can't use either of those for this example. It's got to be the first one. But the first one says sine squared plus cosine squared equals 1, and you just said, Mr. Beckner, that that's cosine squared minus. It's a minus instead of a plus, so how are you going to use a Pythagorean identity? This is how. You only change your cosine squared or the sine squared, which means you're going to have to rearrange the Pythagorean identities. So here's the first variation. Sine squared plus cosine squared is equal to 1. Or, and I'm going to erase the algebraic step, what you could do is subtract cosine squared on both sides. When you do that, you'll only have the sine squared on the left, and on the right you'll have 1 minus cosine squared. Actually, I won't erase it. So you get sine squared of theta is equal to 1 minus cosine squared of theta. So this is an alternate form of that Pythagorean identity. Or, if you took the sine squared of theta plus the cosine squared of theta is equal to 1, you could instead subtract the sine squared on both sides. Again, sorry for the thetas that look like 2's. And you get cosine squared is equal to 1 minus sine squared. That's the other variation. So if you see a 1 minus cosine squared, you could turn it into sine squared. Or if you saw a sine squared, you could turn it into 1 minus cosine squared. Or if you saw cosine squared, you can write 1 minus sine squared. Or if you saw 1 minus sine squared, you can write cosine squared. Now, I said to only change the cosine squared or sine squared. So what I'm saying is you're either going to use this one or you're going to use this one. Now, technically, big surprise, doesn't matter which one you use, but there's an easier way out of the 2 options. The easy one is to replace the one that there's less of. So I have a cosine squared twice here. There's 2 of the cosine squares, but there's only 1 of the sine squares. So it is my opinion that replacing sine squared would be easiest. Did not say it's the only thing, it said it's the easiest. So we're going to replace this sine squared here with 1 minus cosine squared. Now you might be thinking, well, Mr. Beckner, you just gave me 2, arguably 4 more different formulas to memorize. How many formulas are you going to give me to memorize by the end of the semester? No, I didn't. I gave you a formula that I manipulated algebraically. The same idea, how we took sine squared plus cosine squared and turned it into the formula with tangents and secants or cosecants and cotangents. Algebraic manipulations. So you can memorize or you can manipulate. It's up to you. Pick your poison. All right, so the cosine squared, I'm leaving alone. And the minus, I'm not changing the minus, but the sine squared, I'm changing to 1 minus cosine squared over here. What I'm writing is wrong, what I'm writing is wrong, what I'm writing is wrong, what I'm writing is wrong temporarily. Because this minus was applied to the whole sine squared, which is this whole thing. You guessed it, we need a parentheses. Very easy to miss. Equals 2 cosine squared of theta minus 1. Now what we can do is distribute on the left. The minus in the parentheses, I mean, it just seems like nobody's going to want that, so let's distribute it. So we get cosine squared of theta. That's now a minus 1 and a plus cosine squared of theta. The right-hand side I have not changed. It's pretty common that we only deal with one side of the equation, but you can choose to manipulate them and move things. Like I've said, we'll do that next, in the next version of this example, that is. All right, we got cosine squared minus 1. We got cosines, and then plus cosine squared. Cosine squared and cosine squared are like terms. It's apple plus apple. Apple plus apple is 2 apples, so cosine squared plus cosine squared is 2 cosine squared. So all we did here is combine like terms, CLT, combine like terms, blue, which gives us 2 cosine squared of theta. The minus 1 is not changing, so it's back to black. I'm not changing the right side at all. I haven't this whole time. I could have, but holy cow, the left side matches the right side. We're done. QED. So I chose to take what I think is the easier method of just replacing something once. Although a lot of people might go, I do not like this minus there. I know I make that mistake all the time with the distribution. So I'm going to go against your grain, Mr. Beckner, and I'm going to replace the cosine squareds. Okay, fine. So the left side, this cosine squared would be 1 minus sine squared. So you'd have 2 negative sine squareds, which would make a negative 2 sine squared. This on the right side, the cosine squared would also become 1 minus sine squared, but there's a 2 in front of it. So you'll have a negative 2 sine squared, and then a 2 and a minus 1, which would make a 1. And everything works out perfectly. Here's the alternative way, though. So I just described an alternative way, but here's a drastically different way. So cosine squared minus sine squared equals 2 cosine squared minus 1. Let's just rearrange. I'm just going to move some terms. Move things. How? Well, I see sine squareds and cosine squared, so maybe I try and move all the trig terms to one side and all the non-trig terms to the other side, because then maybe I can make it look like this. Maybe I can make it look like that by algebraic rearrangement. So that's a minus 1, so I probably want to move that to make it positive. Don't have to. There's a workaround for that. So let's add 1 to both sides. Then, all right, we have a single cosine squared on the left, but the ones on the left now, we don't want that. We don't want the trig term on that side, so let's move that. Let's subtract cosine squared, like that. And then the sine squared, we're also going to need to move to the right. And you can show this in several steps if you need to. And after you do that, so we have the 1 on the left, the cosine squareds cancel. The sine squareds cancel. So then we just have our equals. 2 apple minus apple is 1 apple. So 2 cosine squared minus cosine squared is 1 cosine squared. I'm not going to write the 1 in front though. The 1's canceled. We have this plus sine squared. And yeah, that is the Pythagorean identity right there. But you're not done. You need to change the right side to be just 1 by Pythagorean. And you're done. QED. Some of you will think the second version's easier. Some of you will think the first version's easier. Some of you will think the first version, but replacing the cosine squares instead of sine squares will be easier. There are so many variations of this problem. I could probably take 45 minutes and just keep doing the same problem. But that would be boring, and we don't have that much time together, as you know. QED. C. Oh, and I wanted to, well, no, I don't. You'll see it. You'll see it. Cosine of theta times cotangent of theta is equal to 1 minus sine squared of theta over sine of theta. All right, so my brain, the way I do things with this is I generally tackle Pythagorean and turn things into sines and cosines first. If I don't see a Pythagorean identity screaming at me right now, then I turn everything into sines and cosines. Or I can just go ahead and turn sines and cosines and still maybe see a Pythagorean identity. Just depends on how you want to approach things. I can manipulate just the left side, I can manipulate just the right side, I can manipulate both. So I'm going to do sines and cosines first. So let's just turn everything into sines and cosines first. That's going to be my choice. And that does not say tangent, that's just me making a little memo that we're changing things to sines and cosines. Well, cosine of theta is cosine of theta. That doesn't change. Cotangent does though. Tangent sine over cosine, which means cotangent's cosine over sine. So that's a change. There's no tangents, cotangent, secants, or cosecants on the right, so I'll leave it alone for now. I will say technically there's a Pythagorean identity in there, kind of just how we were doing in the last example, but I don't want to do too many things at once. All right. Well, cosine times cosine on the left is cosine squared, so you could just say simplify, stack, whatever. So the left now, the top changes to cosine squared. The bottom is still sine of theta. Again, blue for what changed, black for what didn't change. And that's 1 minus sine squared of theta over sine of theta. And even from just this point alone, from this point to finish it, which could be done in probably about 1 to 5 steps depending on your path, I see at least 10 different ways that I could verify this. Notice one thing, the bottoms are the same. Since the bottoms match, all we really need to do is just focus on the tops. Since the bottoms match. We can just focus on the tops since the bottoms match. If the bottoms are the same, that means the tops have to be the same. So cosine squared equals 1 minus sine squared. Again, all I'm focusing my energy on now is just these two things, trying to make them equal. Well, I see sine squareds, cosine squareds, and 1s, so it's probably a Pythagorean identity. So you can memorize the variations, and here's the cool thing about those two variations we just established, these two asterisks. It's always one of them squared is 1 minus the other squared. Sine squared is 1 minus cosine squared is 1 minus sine squared, and that's just because of the simple algebraic rearrangement. When they're on the same side, it's positive 1. When they're on the other side, one of the trig functions has to be negative. So we're either going to use this one or this one. Well, I see cosine squared and 1 minus sine squared, so it's definitely this one. Now I can choose the left side and replace it with the right side, or I can choose the right side and replace it with the left side. There's two options. Doesn't technically matter. So it's Pythagorean. I'm going to replace the left side. A lot of people like to just replace the single term. So I'm going to replace the cosine squared with, what did we say it was? 1 minus sine squared. So 1 minus sine squared over, bottom didn't change, sine of theta. And I'm not changing the right side at all. You don't want to change the sine squared into 1 minus cosine squared in there. You don't change both. You want to have just one of them. If you see a mixture of cosines and sine, sorry, a mixture of cosine squareds and sine squareds. Just change one of them over, not both. And then over the sine of theta. These are literally the same, so you are done. So alternatively, in orange, because this is completely different, when we were at the cosine squared of theta over sine of theta equals 1 minus sine squared of theta over sine of theta. Some people will choose to replace the 1 minus sine squared with cosine squared. So that's the replacement I'll do this time. So blue for what changed. So that would be cosine squared of theta, and then you're done. Some people would have said, oh, you have a fraction equal to a fraction, so cross multiply. Sure, that can get you the answer as well. I'm not going to show all the work for that, though. Some people would have cleared the fractions. Some people would have done, all right, well, I got 1 minus, no, sorry, not that. We got cosine squared over sine equals 1 minus sine squared of theta over sine. Some people would have said, all right, I've got an LCD of sine of theta. So they multiply both sides by sine of theta, wrapping the top in the parentheses because you have to, so that you see the denominators all go away. No more fractions makes the problem a little easier on the brain, right? Oops, too far. There we go. And then what we end up with is cosine squared of theta equals 1 minus sine squared of theta. Then you could literally do the same replacement of the left or the right-hand side. Or you could take an alternate approach and add sine squared of theta to both sides. It looks like 2 theta, not squared. Doing that gives you sine squared plus cosine squared equals 1. And then you're done. As I said, most of these problems have countless ways to verify their identities. The homework kind of forces you into one particular way, but at least it's just a drop down and like a 4-option kind of thing. It's not too bad. It really isn't too bad. It, in my opinion, makes it too easy. Which is why for the next test, I may have like a paper pencil submission problem for a couple of these by themselves, thinking about it. All right, sine of theta over tangent of theta. Then plus cosine of theta over cotangent of theta is equal to sine of theta plus cosine of theta. And again, the real point of all this is that way when you're in calculus and you've got this thing on the left-hand side and it looks like a mess, ultimately you understand that you can simplify it to be something prettier. And maybe you don't know that you can, maybe you're just trying. And then in trying, hopefully you didn't end up with it. Because trying to do calculus with sine over tangent or cosine over cotangent, I don't know how to apply those calculus formulas to that. But I definitely know how to apply the formulas to sine and cosine. So it's very often about cleanup. All right, so there's a lot of things going on with this. There's a lot of different paths. And what's interesting is that most of the paths you'd end up using an LCD because you see fractions, you see denominators. And with a denominator of tangent and then another denominator of cotangent, the LCD is tangent times cotangent. So that's one way you could do things. And I'm going to do that as the alternate method. And what's interesting is that LCD is a lot more simple than it looks. How do I want to do this? I'm trying to decide if I want to clear the fractions or leave the fractions. But we're going to turn everything into sines and cosines first. So that's what we're going to do. Sines and cosines. I don't like looking at all these tangents and cotangents. Let's get rid of them. So that's what one student will think. And if they don't think it initially, they'll probably think it in a little bit of time later. All right, so blue is going to show it changes. So we got sine of theta over, instead of writing tangent, that's sine over cosine. And the plus, we have a cosine of theta all over. And instead of writing cotangent, we're going to write cosine over sine, leaving the right-hand side alone. All right, so this is division of fractions. The black over the blue is division by a fraction. So let's multiply by reciprocals. So change to multiplication by reciprocals. Remember that A over B on top of C on top of D is the same thing as A over B division symbol C over D, which is A over B times D over C. So dividing by the blue is the same as multiplying by flip the blue. So we'll have sine of theta, here's what changes, times cosine of theta over sine of theta. See, this division became a multiplication and we flipped it. That is old school arithmetic, but just with trig functions in place of numbers. Then the cosine of theta from the very top, now we change that to a times, flip the cosine over sine to a sine over cosine equals sine of theta plus cosine of theta. Well, simplify. Sine times sine. Sorry, sine over sine, gone. Cosine over cosine, gone. Wow, we went from a fraction to an even worse fraction to no fractions. How convenient is that? So now this first bit is just a cosine of theta. Again, these two things canceled, leaving just that cosine. Then the plus. Now here, the cosines cancel, leaving just the sine. Then the right-hand side, we have not touched at all. Now, this technically, if you really want to get ridiculously specific and higher math, this is not done because the left side and the right side has a plus b versus b plus a. Nobody cares in trigonometry, though. This is done. This is verified. QED, finito, whatever. Mic drop. You want to see it again? I know you want to see it again. Alternatively, So I mentioned earlier, some students look at this problem and they go, ooh, gross. Tangents and cotangents, gross. I don't like those, so they switch it to sines and cosines. And then, I mean, this is annoying to some of you. Dividing by fractions is multiplying by reciprocals, but annoying is something you'll be tolerating all semester. It's not gonna go away. Other students will look at this and they'll go, ooh, fractions, gross. Let me get rid of my fractions. Let's clear my fractions by finding an LCD and then multiplying all the fractions and terms by the entire LCD. So that's what I'm going to do this time. So I'm going to say my LCD is tangent and cotangent are the only denominators, so tangent times cotangent. Again, I know my thetas look like 2's. I'm sorry, there's no 2's in here yet, unless they're squares. So we multiply all the terms by that. So I'm gonna come in and do that in red after a minute. Leave some space. Leave some space. Some space. Well, I blue for showing the change. So tangent, more space. tangent, cotangent, tangent, cotangent, tangent, cotangent. Old school Algebra 1 technique for getting rid of fractions and equations. Don't ever forget it. If you forgot it, here's your reminder. Don't forget it again. In equations, to eliminate fractions, you find the LCD and you multiply all terms by it. If it's a fraction, they're going in the top. Why are we doing this? For canceling. Tangents go away from the first one. Cotangents go away from the second one. Nothing happens in the right side though. There's no canceling. We're kind of stuck with it. So this term is sine times cotangent. This term is cosine times tangent. So I just want to erase the canceling. So this is now, we said the tangents are gone, so sine times cotangent, or cotangent times sine, the order doesn't matter. Then plus, the cotangents are gone, so it's tangent cosine. Nothing's changing on the right side, so just leave them alone. Tan, cotan, sine, tan, cotan, cosine. Now I'm going to make an observation here at the end of the problem. I'm not going to do it yet, but these two things that I highlighted, I'm going to mention ahead of time. They're equal to 1. Tangent times cotangent is equal to 1. Why? We'll see in a hot second. So those two things that are highlighted are just going to be 1s, and the whole right side is just going to be sine plus cosine again, interestingly enough. But let's see why. All right, this mixture of sines and cotangents and tangents and cosines, I don't like it. I strongly do not like it. Now I definitely want to go to sines and cosines only. So wherever we see a cotangent, I'm going to write cosine over sine, but the sine to its right is left alone. Wherever I see a tangent, I'm going to write sine over cosine, and we leave the cosine alone that was at the end. Tangents, sine over cosine, cotangents, the opposite, the reciprocal, excuse me, cosine over sine. So sine over cosine for the tangent, cosine over sine for the tangent. But that sine at the end of that one is still there. Same thing for this one. Sine over cosine, and then cosine over sine. Leave the cosine alone at the end. So tangent times cotangent in both instances was equal to this thing. Look at what happens to the highlighted thing when you write everything in sines and cosines. You've got sines in top and bottom, they cancel. You've got cosines top and bottom, they cancel. The sines cancel the sines, the cosines cancel the cosines. Just in that section, that sign didn't have a pair to cancel with. So that whole thing goes away, which means tangent times cotangent is actually equal to 1. So that's a property that you could add to your little list of memorization if you wanted. You could go and then say, hey, I just noticed that whenever I have tangent times cotangent, it goes away. It just leaves me with a 1. So this is a really cool property in the same way that sine times cosecant is 1, in the same way that secant times cosine is 1. They're reciprocals. Tangent and cotangent are reciprocals, and by definition, reciprocals multiply, cancel. So that just would have saved you some extensive writing if you noticed that. All right, well, what all cancels? Well, we still know all those are gone, all those are gone. The sines cancel here, the cosines cancel here, and that'll leave us with cosine of theta plus sine of theta equals sine plus cosine. And don't worry about swapping the order. Verified. Now, I know that most people are going to think that that second version, this alternate version, was worse. But maybe you just have the mindset that you don't like fractions. When you see fractions in an equation, you want to cancel them, so you might have done this, and it would have led you down this path. And it really was not the end of the world. Okay, so we cleared fractions, then we went to sines and cosines, and then we just simplified. It wasn't awful. Yeah, we could have saved ourselves a little bit of space because, well, right here and here, we could have went to just saying, hey, they cancel each other out. They cancel each other out. So that's just sine and cosine. It just means we would have saved a little writing over there. It wouldn't save us anything on the left side, though. And what I think is absolutely the most interesting aspect of this whole thing is that this LCD is really just a 1. It's a 1, but you don't want to multiply everything by 1 because it wouldn't cancel the things that you needed to cancel here and here. So it's one of those fascinating things where we are dealing with something much simpler than it actually looks, but we can't think about it in the ultra simple way until a little bit later. Otherwise, it screws some things up. About 20 minutes left. Okay. Again, if you didn't like that way, we turned everything to sines and cosines first, and then we had some baby arithmetic to remember, and it ended up being pretty simple after that point. But I know a lot of people will stall out at this point, and you can't. That issue is going to come up several more times throughout this course. I know I'm a broken record, but I do that for a reason. All right, so that was it C or D? D. So now we're up to E. Got cosecant squared minus, oops, I forgot my C for some reason. Cosecant of theta times cosine squared of theta is equal to sine of theta. Another case of really, really ugly on one side and really simple on another side. So again, in calculus, maybe you've got this thing and you've got to do calculus on it and you go, I have no idea what to do there. Well, just try some algebraic and trigonometric simplifications, that basically the things we're doing along the way here. And just hopefully by the end you get to be a sine and boom, you can do your calculus. Maybe you're taking its derivative and then the answer is cosine. Maybe you're integrating it and the answer would be negative cosine, oddly enough. Don't worry about what I just said. That's not trig stuff, that's calculus. So maybe you say, ooh, I don't like these. I want to turn everything into sines and cosines. That would be a solid approach. Maybe I'll take that as an alternate approach for the first step later. But for now, I want to focus on something a little different. This term and this term have something in common. Again, the whole term is including the cosine squared, but I've underlined what they have in common. They have a common factor. And I mentioned in those instructions earlier, and this is something we haven't done yet, which is why I want to focus on it, that factoring can quite often be helpful for this stuff. Whether it's easy factoring like a GCF or maybe a difference of squares or some trinomial thing like grouping or trial and error or box method, whatever you understand and know, because I'm not here to teach factoring. So there is a GCF here, and that GCF is cosecant of theta. You can't say cosecant squared because while this one has 2, I circled the wrong thing. This does not. So you can only take one of them away. So in blue, I'm going to write the cosecant of theta. That's our GCF. Then we open a parentheses and we divide each term by what we're dividing out. Don't overthink this. Just because these have multiple letters, it does not affect the factoring at all. Think about if you had this to the side. If I had a squared minus ab squared, I would take out an a and that would leave me with a minus b squared, because you take away an a from each of the terms. That's the exact same thing as what's happening over here. It's just a is cosecant and b is cosine. So cosecant squared, taking away one of them, leaves us with one of them. Not the 2 I was looking at, sorry. Then minus, taking this cosecant away, it's the only one, so we don't have it, but we still have the cosine squared. If you don't trust this, distribute it, you'll get the original line. But obviously, don't redistribute it, because we did that for a reason. That would just be to check yourself. All right, right side's too simple, we gotta leave it alone. So we got cosecant times cosecant minus cosine squared. What did I write wrong here? I have an error. When I was looking at this problem, this 2 was, I was looking at the 2 on the cosine. It wasn't supposed to be there. I apologize. I need to erase this bit right here. This was not supposed to be there. All right, so please, everyone, please pay attention to what I'm about to change. That's just supposed to be a cosecant, not a cosecant squared. Sorry for that. Which means factoring it from the first term will change it. So there was only a single cosecant squared, which I've taken, which means there's nothing left there as a factor, but we can't put 0 there and we don't leave it blank. It's 1. So again, please note that I changed this from cosecant squared to cosecant, which changes this inside the parentheses. Again, I apologize for that. If I don't make that change, this won't be a verifiable identity. This is what happens when your vision sucks and you talk and write and think all at once. All right, so hopefully we've got those changes now. Okay, well, I see a 1 minus cosine squared. So in my brain, whenever I see that, I go, ooh, Pythagorean's a good idea. I also see a cosecant, so in my brain I'm going, ooh, changing the sines and cosines would be a good idea. And again, I could have still done that in the original line. I could have changed the cosecants to 1 over sines. That wouldn't have been wrong. So what do you think? Sines and cosine change first or Pythagorean? I tend to leave Pythagorean for later. So let's change into sines and cosines, which means we're only going to fix up this thing. Cosecant is 1 over sine. So this will be what just happened. What's going on? 1 over sine of theta. Then the things that haven't changed at the inside, which is 1 minus cosine squared of theta equals sine of theta. Now, some people might say, all right, we'll distribute the 1 over sine, and that's fine. Some people might say, well, hey, I got a fractional equation. Let me multiply both sides by sine, so they'll cancel on the left, and you have a sine squared on the right, and that's fine. But the thing I'm going to focus on is Pythagorean. So there's 2 different things I could do here. I could change this cosine squared. I could, but I'm not gonna. I could change cosine squared, where is it from earlier, to 1 minus sine squared. That's an option. But what I generally like to do is if I see it already in the 1 minus, then the squared trig form, I try to replace the whole thing instead. Again, it would not have been wrong, but I just think this is easier because then you don't have to worry about this negative and distributing negatives and all that jazz. So I'm going to replace 1 minus cosine squared. Going back to that list earlier. Now, I'm not going to use the bottom one now because that's 1 minus sine squared. I got to use this one. 1 minus cosine squared is sine squared. So that left side parentheses is sine squared. So we have 1 over sine. That was blue before, now it's black because it didn't change. But this 1 minus cosine squared is now sine squared. Again, if you replace the cosine squared with 1 minus sine squared, you'd have to distribute the negative and you'd cancel ones and then you'd get it anyways. Equals sine of theta, that shouldn't be blue. And then you can just simplify on the left side, reduce, however you want to say that. And you'll end up with, you get one of the signs canceling, so that's now a sine of the first power in the top. So the left side is sine of theta, because we had the 2 canceled down to 1. The bottom's gone now. The right side is sine of theta, which is still black. We didn't change it. Those match. We're done. An alternate form of this one. Gonna go a little quicker. Cosecant, see, I'm trying to do that square again. Cosecant of theta minus cosecant theta cosine squared of theta equals sine of theta. All right, so I'm gonna be the student who just hates cosecants and tangents and all that, so I switch to sines and cosines immediately. So each of these cosecants is 1 over sine of theta. Now, the left side, you've got a couple options. These are 2 separate fractions with a common LCD, so you could combine them. Or you could say, hey, I've got denominators and fractions. I hate fractions, strong word, but many students hate them. So maybe you do your LCD and you eliminate the fractions. So you go sine of theta, sine of theta, sine of theta. So the red's me showing the LCD. That was 1 over sine of theta for the first term. This was 1 over sine of theta cosine squared for the second, and then sine for the third. Then you get to cancel. Sines are gone, sines are gone. Which will give us 1 minus, those are all gone, we're just left with the cosine squared there, equals sine times sine is sine squared. And we've already seen this several times already. You could add cosine squared to the other side, and then you see the direct Pythagorean identity after you change the right side. Or you can just change one of the sides, but either way, ultimately you'll have to use Pythagorean. Again, my personal favorite is to make the more complicated side simpler. 1 minus cosine squared is sine squared. I'm not changing the right side the way I've done this. And we're done. Again, I could have added cosine squared to both sides. That would give me 1 equals sine squared plus cosine squared. And then the right side I would change to 1, and we'd be done. Technically, you can change the 1 to a sine squared plus cosine squared. You can make it look uglier, but we tend to like to make things look simpler. That's the primary point of all this. All right. I think we have time for just one more. We'll not be done with this section for the day. We will have 1, 2, 3, at least 4 more after this. Next class. 1 minus sine of theta over cosine of theta equals secant minus tangent. You can't cross multiply this because it's not fraction equal to fraction. You could say, hey, there's an LCD of cosine and multiply the left and right side by cosine. And that would be a great method. I'm going to do something we haven't done yet, though, just again to show you that different things can work. Let's split. This was one of the instruction ideas, very beginning, that if you got a fraction, maybe you just like splitting fractions. Or if you have multiple fractions, maybe you like combining fractions. Those 2 steps can work. Sometimes they're good ideas, sometimes they might complicate things. All right, so that means I'm going to change the left side to 1 over cosine of theta minus sine of theta over cosine of theta. I'm not going to mess with the right side yet. Maybe you said, hey, I'm going to change everything to sines and cosines first. Then your right side would have changed and your left side wouldn't have changed. It's up to you. This requires good algebra skills and good memorization of your trig properties. Now, again, I could clear the fractions if I really wanted to, but I'm going to turn everything into sines and cosines, which means the secant changes to 1 over cosine, the tangent changes to sine over cosine. So the left side I'm not messing with yet. And you might say, well, hold on, Mr. Beckner, I recognize that this is secant and this is tangent. Couldn't I change those? Yeah, absolutely you could. The list I gave you were things that work generally, but not the end all be all. If you really want to change things to secants and cosecants and tangents and cotangents, be my guest. But you're definitely the odd person out. So secant is 1 over cosine. And minus. Tangent is sine over cosine. And look at that, we're done already. The left side matches the right side. That's not a question mark, that's an exclamation mark. Alternatively, I know y'all love me for that. Love's a strong word, I'm sure. 1 minus sine over cosine, secant minus tangent. Maybe you went ahead and did the sines and cosines first. So that's 1 over cosine of theta, and then minus sine over cosine. And then you say, well, hey, I've got an equation, I can get rid of the fractions. With the LCD, the only denominator we see is cosine of theta. So you do that, you multiply here by cosine, here by cosine, and here by cosine. I'll put it in the back. So the cosines cancel here, and here, and here. And it gives you 1 minus sine of theta equals 1 minus sine of theta. And then you're done. Or you could have said, another alternate approach, just starting from here, from the 1 minus sine of theta over cosine of theta equals, after you did the sines and cosine stuff, 1 over cosine of theta minus sine over cosine of theta. Maybe you say, well, hey, these two things have a common denominator. Maybe we combine the fractions. I said some people like to split, some people like to combine. So someone could split the left side and they'd be done. Someone could combine the right side and they'd be done. It's up to you. But that would then be 1 minus sine theta over cosine on the right. The left doesn't change. And you're done. See, that's why I said these things are options. They're not end all be all, they're things that help you. One student might split the left side and they're done. One student might combine the right side and they're done. Maybe you don't do either of those two things. Maybe you change the sines and cosines and then LCD it and you're done. Solution process can be similar between methods, but it can also be drastically different. It just depends on the problem. That's, again, what I don't like about the homework is it gets people caught up on just doing it one specific way, when in reality, almost all these problems have more than 5, 6, 7 ways to actually get the job done. And in fact, you can extend that and say every single problem has a million different ways to do it because you can just do arbitrary steps. So we're going to do, like I said, 3 or 4 or 5 more. I don't remember what the number was next class. So we're not done with this section. We will come back and do more. We're going to change up a couple of details, and it won't always just be theta anymore. We're going to invoke a few other ideas, more factoring stuff. We'll see that next time. For now, your last reminder, oh, I closed it, is that the test is Wednesday, Thursday of this week, which are the 14th and 15th. So it goes live at 12 a.m. Well, let's say 12:01 a.m. just to be safe on October 14th, and it will close out after 11:59 p.m. on Thursday the 15th. You have to submit your work in Canvas within 15 minutes. I will have that location up by Wednesday. It's not there yet. I will put it at the top above the recorded lectures section. If you do not turn your work in, if you do not take a picture of your work and submit it to me, I can go back and give you a 0, because this is not a class where you can do all this stuff without showing any work, unless you were just absolutely brilliant. And if that's the case, then maybe we need to have a personal conversation and ask, why are you in trick? All right, jokes aside, Have a good one. Remember that the review is in the homework section right under 5.8. You don't have to do this one. It won't hurt you grade-wise or help you grade-wise, but I highly recommend it because the questions I put on the test will bear resemblance to the questions on the review, and that I promise you. Have a good one. We'll see you on Wednesday. Take care.